Hello everyone and welcome to the Unit 12 review session. I thought I would do one of these review sessions just like I do at school and record myself going through the review session problems. Before we get this started, just to make sure that you guys are all up to date with what you should be doing, the first thing you should have done is watched my video from last week of finishing up those notes for the unit. Done the 2 practice sheets and checked your answers. Finally, we did put that check for understanding on the MyMCPS's practice quiz, and that's a really good place to get a feel for what your test is going to look like. In addition, there is your typical review sheet with answer key that is on MyMCPS, and also this review session sheet for you to print out if you would like to. So let's go through the different sections. All right, for part 1, we're going to choose whether these things are going to cause an increase, a decrease, or if they're going to remain the same. As the temperature of a liquid increases, the vapor pressure of that liquid. So let's just review a little bit when we're talking about vapor pressure. When we're talking about vapor pressure, we're talking about a substance that really is a liquid, all right, typically at room temperature. And we have to remember that all liquids are constantly moving, and those molecules that are on the surface, some of them are going to actually change into, and this happens at all different temperatures, they're going to change into a gas. All right, as we increase the temperature, that means that we're going to be increasing the motion of these particles. So they're going to be moving faster and more of them will turn into a gas. All right. The more gases we have, the more chances they are that they're going to hit the sides of the container, which is going to cause an increase in pressure. So as the temperature of the liquid increases, the vapor pressure of that liquid will increase as well. All right. Another thing we like to link with vapor pressure are the attractive forces between the liquid molecules. By attractive forces, we're talking about intermolecular forces. All right. The stronger, remember we're talking again about this liquid, and the molecules on the surface. The stronger the forces holding these molecules together, all right, the fewer will actually turn into a gas. So if you have something with a very strong intermolecular force, you're not going to get a lot of gas particles, which means you're not going to get a lot of pressure. So as those attractive forces increase, they're holding on to that liquid, and therefore the vapor pressure is going to decrease. All right. At number 3, as the attractive forces between liquid molecules increases, again, we're talking about strong intermolecular forces. What's going to happen with the boiling point? Well, when we're talking about boiling point, we're talking about when the vapor pressure of that liquid equals atmospheric pressure. All right. Okay. And if you have strong attractive forces, strong intermolecular forces, it's going to take a lot more energy in order for you to get that pressure up to atmospheric pressure. Again, because those molecules want to stay together and you have to get them moving even faster, it's going to take in more energy to turn them into a gas. So as the attractive forces between liquid molecules increases, the boiling point will increase too. It takes more energy to change the state of that particular substance. Therefore, a higher boiling point. All right, so let's move on to our next section, which has to do with this graph here. Oh, I didn't mean to write right through that. This is our phase diagram. Okay, and remember, when we're looking at any phase diagram, it's going to be broken up into 3 parts. Farthest to the left, you can think of your coldest temperatures, are your solids. Farthest to the right, all right, are going to be your gas. And in the middle is the liquid state. Okay, and it makes sense. As temperature increases, we typically go through solid, liquid, and then gas, depending on the substance. Okay. All right, so let's look at some of these questions. Which phase or state is represented by Y? All right, so Y is right here. This is your gas area. And again, we know it's the gas. It is the farthest to the right. It is the area that, for the most part, has your highest temperatures there. All right, what is the normal melting point? When we say normal, we mean at standard pressure. all right? And standard pressure is, all right, 101.3 kilopascals, which is the same as 1 atmosphere, which is the same as 760 millimeters of mercury. All right, great. So what is the normal melting point? Well, normal, again, this graph is in atmospheres, so that means at 1 atmosphere. Melting point, when we're melting, that means we're going from a solid to a liquid. So all along here, you'd have your melting points, solid to liquid. Normal refers to at 1 atmosphere. So I'm going to go here and I'm going to say that's right around 10 degrees Celsius. All right. What is the normal boiling point? Well, when a substance boils, it means it's going from a liquid to a gas, which is represented along this line. This is your vaporization line. Again, at 1 atmosphere because of normal. And I'm going here and I'm going to say that's probably about 45 degrees Celsius. All right, great. What temperature in Kelvin and pressure in kilopascals is the triple point? So remember, triple point is the temperature and pressure where you're going to have all 3 states of matter existing. And on this graph, it's represented by letter Z, and it's the point where all 3 of your lines come in. All right, so here, let's just say for argument's sake, we're at 0.5 atmospheres. All right, so our triple point is 0.5 atmospheres. And I'm going to say probably about, I don't know, 8 degrees Celsius. Now in this question, and as you saw on your check for understanding, make sure you're watching those units because in some questions I'm going to want you to convert. And in this case, I do. I want to know what the temperature and pressure are. I want the pressure in kilopascals and the temperature in Kelvin. All right, so we're going to convert our 0.5 atmospheres. I love factor labels, so we're going to go ahead and do that to kilopascals, 101.3 kilopascals for 1 atmosphere. All right, I'm going to punch that into my calculator. Boom, right here. And 0.5 times 101.3 divided by 1. So that's going to be 50.65 kPa. All right, so 50.65 kilopascals. And then for temperature, remember to go from Celsius to Kelvin, you're just going to take that Celsius temperature, which I have here is about 8 degrees. You're going to add 273 to it, 8 plus, I'm not used to this calculator, 8 plus 273, I certainly should be able to do that in my head, is 281 Kelvin. All right, so there are your answers to number 7. Finally, for this graph, what state will this substance be at STP? Well, when I'm talking about STP, that stands for standard, temperature, and pressure. All right, we already talked about what standard pressure was right over here. So we know the pressure that we're going to be dealing with on here is 1. All right, and standard temp is 0 degrees Celsius. So if I go to 0 and I go up to 1, I'm kind of right where that W is, and that means that I am a solid. All right, great. Okay, so let us move on to the last part of our review, and that is looking at a vapor pressure curve. All right, this time on our curve, we have temperature, degrees Celsius there on our x-axis, and we have our pressure in millimeters of mercury. You will see all 3 types of pressure, so don't worry if that happens, okay? All along these lines, that represents the vapor pressure of that particular substance at that temperature and pressure. Let's look at letter A. What is the normal boiling point? So we already mentioned normal means it's standard pressure. Well, standard for millimeters of mercury is 760 millimeters of mercury. So 760 is going to be about here of liquid Z. Okay, so I'm just going to go liquid Z, I'm right about here. And again, we're kind of eyeballing. So I would say about 65 degrees Celsius. What is the vapor pressure of Z at 75 degrees Celsius? All right, so you're going to go to 75, which is about, I'd say here. And we're going to go up, and we're going to say probably about 1,200 millimeters of mercury. All right. We often use vapor pressure curves to answer questions like C. Which liquid exhibits the greater attractive forces between molecules? All right, so when we're doing that, we want to see, all right, which one takes more energy to vaporize. The one that takes more energy to vaporize, all right, has the stronger intermolecular forces. And in this case, looking at this graph, all along, in order to get sort of equal pressures, you have to get X up to be a higher temperature. So X has greater attractive forces, all right? X would also have higher boiling points at any pressure, and that's another way of thinking of it, okay? All right, guys. Well, I hope you enjoyed this review session. I know you guys are going to do really great. Remember that your test is going to be all multiple choice questions, and it is open note. All right, but please, it is not open cell phone, so no communication when you're taking the test with your friends. Use your notes, use this practice sheet, all of that good stuff. If you have any questions, please email Miss O'Donoghue. I hope you are doing well, and you will hear from me soon. Take care. Bye-bye.